The very first thing that you learned how to do in pre-AP chemistry was how to write reactions from word equations. The types of reactions that we looked at earlier on in the year were synthesis, decomposition, and single displacement reactions. And we looked at a number of specific scenarios where you would need to be able to predict the products. Since then, and particularly in the solutions unit, we've looked at several double displacement reactions, specifically reactions where a precipitate is formed or acid-base reactions. What we're going to look at in this lesson is those reactions in particular, with a couple of additional double displacement reactions that specifically have gases produced, and then we're going to look at how to take all of these kinds of reactions and examine them as net ionic reactions. So first of all, to review, when you have a double displacement reaction, they tend to occur in aqueous solutions. And what you have two compounds reacting, both of which are ionic, that consist of a positive and a negative ion. And what happens in these reactions is a double displacement whereby the cation from one of the reactants combines with the anion from the other reactant, and the other two ions join as well. The biggest thing that you need to pay attention to is the charges on the ions when you form the products. So let's look at an example here. We've got a reaction where we've got calcium sulfate reacting with sodium hydroxide. And the products of this reaction were formed by taking the calcium ion and combining it with hydroxide, and the sodium ion was combined with the sulfate ion. Now you'll notice that the charges were considered. The charge on the calcium is 2+, and the charge on the hydroxide is -1, so therefore the formula of the calcium hydroxide that's produced is CaOH2. The sodium sulfate that is produced here is Na2SO4 because the charge on the sodium is +1 and the charge on the sulfate is -2. The solubility rules are used to determine the precipitate, and the equation is balanced using our normal rules. Now, reactions that we've mentioned in passing, but we haven't looked at specifically, are ones where a gas is produced in a double displacement reaction. We've discussed the fact that an acid will react with a carbonate to produce carbon dioxide and water, but we haven't yet showed how you can actually decide that the carbon dioxide is being produced. When you encounter this kind of reaction, so something like hydrochloric acid reacting with sodium carbonate, it looks as though it might be a normal double displacement reaction. So in this case, the chlorine will combine with the sodium to produce sodium chloride, and then the hydrogen will combine with the carbonate. And when hydrogen and carbonate are joined to make a formula, the formula that you would make is H2CO3. And the reason for that is that the charge on the hydrogen is +1, and the charge on the carbonate is -2. So when we do the crossover method, we get the formula H2CO3. Now what you need to recognize is that H2CO3 is not a stable compound in solution. But what will happen is this will further decompose into H2O and CO2. So whenever you do a double displacement reaction and you see that you've produced H2CO3, what you need to do is further decompose it into these two products. So the actual products are CO2 and H2O. Similarly, we can produce ammonia and water in a double displacement reaction. And that comes from recognizing that ammonium hydroxide is not an ionic compound that will exist in solution, but instead this will, like H2CO3, decompose into NH3 and H2O. NH3 is ammonia, which is the gas that you smell if you use Windex or if you go to a hair salon and you smell that smell in a hair salon is the ammonia that's in the air. So when I look at this reaction here, and I've got an ammonium chloride reacting with sodium hydroxide, it looks like a straightforward double displacement reaction. The NH4 plus and the OH minus will combine to make NH4OH, which further decomposes into NH3 and H2O. And the other ionic compound just stays as is as NaCl. And this particular reaction is a 1-to-1 ratio across. Other gases that you might see being produced are hydrogen sulfide if you react an acid with a sulfide, or if you react a sulfite salt, so that's an SO3 salt, like sodium sulfite, with an acid, you would produce SO2. These ones will be less common, and the ones we should focus on at the moment are recognizing these two above. The third type of reaction that's double displacement that we've been working with are acid-base reactions. So an acid-base reaction where we produce water and a salt is really a double displacement reaction, where the H from the acid combines with the OH from the base to produce the water, and then the other ions form a salt or an ionic compound. So when nitric acid and potassium hydroxide react, we produce water and potassium nitrate. Now what we really want to be able to do is take these reactions and write them as net ionic equations. And we'll investigate what that means as we proceed. In order to prepare a net ionic equation, we're always going to start with the molecular equation. Then we're going to break it down into an ionic equation, and then finally finish up with a net ionic equation. The reactions that you've been using all year are molecular equations. So they're defined as an equation where all the compounds are written in full form with their states properly labeled. So as an example, if we have the reaction of copper sulfate and sodium hydroxide, both solutions by the solubility rules, if we look at the products of the double displacement, we'll produce sodium sulfate and copper hydroxide being a solid, and sodium sulfate being aqueous. This, properly balanced, has a 2 in front of the sodium hydroxide. So let's practice with this one here. We've got barium nitrate and potassium sulfate. So to write the products of this double displacement reaction, we're going to make barium sulfate. Barium has a +2 charge, and sulfate has a -2 charge, so we produce BaSO4. And the other product here is potassium nitrate, which is KNO3 because the potassium is +1 and the nitrate is -1 in its charge. Now when we look at the solubility rules, we will see that barium nitrate is soluble because of the nitrate. Potassium sulfate is soluble because of the potassium. Therefore, this one is also going to be soluble by those 2 ions. And the barium sulfate here is a solid by the solubility rules. Sulfates being soluble, and barium is one of the exceptions. The nice thing about these is if you know your basic rules, then, and you know a precipitate has formed, then you can sort of presume that the precipitate must be barium sulfate. And you might not know the rule for sure, but if you know a precipitate has formed, you can be pretty much guaranteed that that's going to be the one. Now to balance this, we need to put a 2 in front of the potassium nitrate. So this is a molecular equation. This is a kind of equation that we're used to working with. Now when we look at an ionic equation, what we're doing is we're looking at a zoom in of the reaction that we're studying. So what we want to do is we want to zoom in on the beaker where the reaction is taking place, and we want to look at how the substances appear in that solution. And so what we need to do is use our knowledge of previous chemistry, knowing what it means when something is dissolved. You know that if a salt dissolves in water, what it actually does is break up into its ions in order to dissolve. So when we look at something like sodium sulfate, which is aqueous or soluble in water, what's actually in the solution are sodium ions and sulfate ions. And when this particular substance breaks up into its ions, it's going to produce 2 sodium ions and 1 sulfate ion. So if you were to zoom in and look at a solution of sodium sulfate, you wouldn't see sodium sulfate particles, you would see sodium ions and sulfate ions. So in the first example where you had the copper sulfate, which is aqueous, copper sulfate actually exists as copper ions and sulfate ions in solution. And the sodium hydroxide that was in the solution actually exists as sodium ions and hydroxide ions. The sodium sulfate, as previously discussed, exists as sodium ions and sulfate ions. The copper hydroxide, though, being a solid, is going to exist as one substance. So if you imagine a beaker, what you're going to see in this beaker is you're going to see a precipitate of the copper hydroxide. And then in the solution, you're going to see the sodium ions and the sulfate ions. So this is sort of the after. And before the reaction occurs, you see the copper ions, the sulfate ions, the sodium ions, and hydroxide ions. I haven't left myself enough room to draw it there. So before we do an example with our reaction, let's just go and do some practice of breaking up the ions and making sure that we can do that step. Because that's really, out of everything we do in this lesson, that's the biggest new skill that we're learning. So further along in your notes, you have these practice questions where you're to practice breaking up the compounds into their ions. And notice in the question it says, where appropriate. So we need to think about this. Okay, so if you have something like sodium nitrate, okay, sodium nitrate is aqueous, so that means that it will dissolve and it will break up into its ions. The ions that it will break up into are sodium ions, and nitrate ions. Now we need to account for the coefficients here. So if I have 3 sodium nitrates that dissolve, I'm going to have 3 sodium ions and 3 nitrate ions. So it's a bit of a two-step process. You want to break up the ions, just like you would in order to do the reverse crossover method, and then you're going to apply the coefficient to make sure you have the correct number of ions. Let's look at this next example. Calcium chloride. This is aqueous, so it dissolves in water. So this will exist as calcium ions and chlorine ions in solution. We do the reverse crossover method, and we see that calcium has a 2+ charge, and chlorine has a -1 charge. So these are the ions that exist in solution. And let's look at how many ions there are. If I break up 2 calcium chloride compounds, I've got 2 calcium ions, and I've got 4 chlorine ions in solution. Let's look at another one here, potassium sulfate. When potassium sulfate breaks up, it breaks up into K+ and SO4 2-. I have 1 potassium sulfate, and it's going to produce 2 potassium ions and 1 sulfate ion. You can see why knowing your polyatomic ions is really helpful for doing this, because you can really confidently break up the ions and know their charges. This next one here, lithium phosphate. So lithium phosphate breaks up into lithium plus and PO4 3 minus. There are 3 lithium ions and 1 phosphate ion. Now this one here, 2 aluminum hydroxide, and it's a solid. A solid will not break up into its ions. So how it would exist in solution is as is. It doesn't break up into any ions. If you were to zoom in and look, you would see compounds of aluminum hydroxide in the container. This one here, CH3COOH. This is a little bit more advanced, but it's important to start learning how to recognize that this is a weak acid. So first of all, it's molecular. It is soluble in water, but it's molecular, and it's a weak acid. And weak acids, as you know by definition, do not dissociate very much in water. So when we encounter them in a molecular formula, and we're moving into a net ionic formula, we won't break it up into its ions. We'll keep it together as a molecule. NH3 is a gas. This is another substance that will not break up into any ions when in solution. As well, H2O as a liquid. It's a pure substance, and it won't dissociate into any ions for these purposes. So the substances that you're going to break up are going to be soluble salts, and if you have a strong acid or a strong base, those will dissociate. Anything else will stay together as a molecule. So this was the equation that we are working from. This is the molecular equation, and when we want to write the ionic equation, what we need to do is systematically break anything up that needs to be broken up into its ions. So for each substance, we decide if it's broken up, and then we'll break it up with the appropriate coefficients and charges. So this one here, barium nitrate, is aqueous, so it will break up. The ions that it breaks up into are barium 2 plus and nitrate. I've got 1 barium nitrate, so I've got 1 barium ion, and there are 2 nitrate ions. Next one is potassium sulfate. This breaks up because it's soluble. It will break up into K plus and SO4 2 minus. There are 2 potassiums and 1 sulfate. This next one here, I've got potassium and nitrate that are soluble. So I have K plus and NO3 minus. Because I've got 2 KNO3, that gives me 2 potassium and 2 nitrate. And my barium sulfate will, barium sulfate will stay together as a solid. So this is my net ionic equation. I'll know that I've done the breaking up properly with the correct coefficients if it remains a balanced equation after I'm done doing the net ionic equation. So the barium, there's still 1 on each side. The nitrate, there's still 2. Potassium, there's still 2. And the sulfate, there's still 1 on either side. This is an ionic equation. Shows appropriately the ionic compounds that are dissolved in water broken up into their ions. So it shows the reality of what it would look like if everything was dissolved in water. Now in a net ionic equation, what we're doing is focusing on what has been involved in the chemical change that has occurred. What we're going to do is we're going to remove what are called spectator ions from the ionic equation in order to focus on what substances have changed. and which ones are involved in the chemical reaction. A spectator ion, much like a spectator at a basketball game, is something that is simply watching the chemical change occur. They're not involved in the chemical reaction. They're the same before and after the reaction has occurred. So when we look at our original example of the copper sulfate reacting with sodium hydroxide, we can see that before and after the reaction, the sulfate has remained the same, and the sodium has remained the same. The copper ions are now part of a precipitate, so they have changed. The hydroxide ions are now part of the precipitate, so they have changed. But the other ions, the sodium and the sulfate, have not participated, and they are simply spectators. So we remove the spectators, and what's left over is our net ionic equation. So in this case, the copper ions are reacting with the hydroxide ions to produce copper hydroxide. Look back at your previous example. Can you identify what the spectator ions will be? You want to look for the ions that are the same before and after the reaction. They look identical on both sides of the reaction arrow. Hopefully you can see that it is the potassium ions and the nitrate ions that are our spectators. And we can remove those, and when we remove them, we are left with barium 2+ plus sulfate forms barium sulfate solid. Now these ions are still aqueous. They were aqueous from the beginning, just means it's dissolved in water. So to properly label a net ionic equation with the states, we'll list them as aqueous for the barium and the sulfate, and we'll put the S because the barium sulfate is our solid. So that's how you produce a net ionic equation. The next examples that you have to practice are in question number 2. And the steps to going from the formulas, the names of the reactants, to the net ionic equation are given. So the very first thing that you need to do is to write the formulas for the reactants. And you need to properly identify the charges on the ions and properly make the formula. So we're going to do B here as an example, if you'd like to follow along. But before we do that, we'll just remind you of the charge on silver here. So silver, you'll remember from our little pattern, if you look at aluminum, it has a 3+ charge, and then the zinc is +2, and the silver is +1, if you look diagonally down. Okay, so that one is a little bit of a simpler example. So the one we'll do together is with lithium carbonate and calcium chloride. What I like to do for these is actually just write out my ions at the top here before I get started, because then I'm set to go for my double displacement as well. So the ions that I'm dealing with are as follows. So my reactants are lithium carbonate, which is Li2CO3, and calcium chloride, which is CaCl2. Okay, and both of these, by the solubility rules, are aqueous. And double displacement will allow me to join the lithium and the chlorine to produce LiCl, which is also aqueous because of the alkali metal. And my other product is calcium carbonate, which by the solubility rules is a solid. To balance this, I need to put a 2 here, and I've got a balanced molecular equation. So I've written the formulas for my reactants. I've written the formulas for my products. I've identified the states using the solubility rules. Now, to identify the spectator ions, I need to write my ionic equation. So for this one here, it's aqueous. It breaks up into 2 Li plus and 1 CO3 2 minus. Calcium chloride produces Ca2 plus and 2 Cl minus. The lithium chloride produces lithium plus and chlorine ions, and the calcium carbonate, being a solid, stays together. So this is my ionic equation. And I'm confident that I've done the correct ionic equation because it remains a balanced equation. Step 4, I need to identify the spectator ions, which are lithium and chlorine. And so I'll remove those to write my net ionic equation, which is calcium 2 plus carbonate gives me calcium carbonate solid. So this is my net ionic equation. Now, a couple questions that you might have are, do we need to put the states in our ionic equation? The ionic equation is really an intermediate step. Okay? These are the more important equations, the molecular equation and the net ionic equation. So those are the only ones that I'll ask you to record the states. And the states will just be the same as what they would be in the original molecular equation. So the calcium is aqueous and it's still aqueous. The carbonate, still aqueous. That's how I knew that it was AQ. Another question that you might have is whether it matters how we write our reactants here. For example, could I write carbonate plus calcium ions give me calcium carbonate? And that's totally fine. What you'll see is that I'll have a tendency to write it this way, with the positive ion listed first and the negative ion listed second, just because that's the way that we write the ionic compound in the end. It's more for form than anything. A plus B is the same as B plus A, though, so it doesn't matter if you write it in the opposite order. And that concludes this lesson.